All right, so welcome back. We are going to proceed with lesson 1.2, which is dealing with graphing motion and kinematics ideas. Going through your slides, again, there are some links here. If you want to get some extra help or support, you can do that, but we'll just continue and get into the lesson. So remembering back to the last lesson where we talked about motion and the concepts of distance, displacement, speed, and velocity, we looked at these types of graphs where it's a motion map or a motion diagram where the dot represents the object, and you can see the space between equal increments of time going by. So every time you see a dot, that's one increment of time. So looking at this, you can see that this car is covering a bigger distance each increment of time that goes by. So we would call that car speeding up. So that's just a quick example review of what was going on last time. And we're going to apply that and just see if we remember anything. So looking at this diagram, it says that we are supposed to decide which one of these four motion diagrams represents this motion. So a bicycle is moving left with an increasing speed. So I think we can eliminate some right away because moving left is only displayed in two of these. So that is not left and that is not left because the arrows are pointing to the right. So it's either B or C, and we want to see speeding up. So we just talked about speeding up. As you speed up, the space between the dots should increase. So it's going to be D here for what we're looking at. I'm sorry, B, what we're looking at. So that's the correct answer. C, going back to C, is actually slowing down. So it's got the biggest distance covered in an equal amount of time. It gets smaller and smaller, so that's slowing down. So we're going to take that kind of concept and idea of looking at these motion maps and diagrams and apply it to graphing. So when we talk about graphing, you guys are familiar with graphing from math class. So again, we talked about this last time with coordinate systems. So we got our X and Y axes. So this slide is just going over positive X's to the right and negative X to the left. That's the type of motion we're going to study first, is horizontal motion or left to right motion. Eventually we'll get into free fall or vertical motion, where it'll be positive Y and negative Y. So again, just where a location is based on a frame of reference or coordinate system. So so taking a look at this one, we are looking at this motion map down here where the dot represents an object's motion, and it has several different kind of ideas happening at once, where in the beginning it looks like it's going at a constant rate, and then that rate changes. So I'm going to put a line here. The rate changes because you can see the spacing is different, and then it changes again. So we have kind of three sections on this graph, and this motion map is going to be displayed on this position versus time graph. So this is a X versus T, that's the title, so position versus time. X because it is the X direction that we're changing the position of, and T for time. So the position X is located in meters, so it's just showing you the location of this object at any particular point in time from 0, it looks like, up to, if we count one, or this is 0, 1, 2, 3, 4, 5, 6, so I'll just highlight 3 and 6, and then 7, 8, 9. So the last moment of data that we have is happening at 9 minutes. So so we're going to kind of examine the graph, or the motion map first, and then we'll apply it to a graph. So we already broke it up into three sections. So there's one section there. I'm going to label that A. There's another section here. We'll label that B, where the dots are close together, and then the dots are spread out the most in section C. So based on that information and just that visual, we should be able to decide which one has the greatest velocity and which one has the smallest velocity. So we did this already with the first example that we had. So the larger the velocity, the bigger the space between the dots, and that would be C is the largest. And then A is the next largest, and then B is the smallest. So trying to write with a mouse isn't that easy, but we'll do okay. So that's just the ranking. So we're going to apply this and take this information and kind of look at it on the graph, on the position versus time graph. So this is the position versus time graph for the same information. We said the first 3 minutes, so 0, 1, 2, 3. This is 3 minutes. That section was A. So that line, or those dots, are representing A. Then the next 3 minutes, 3, 4, 5, 6, from here to here, that's representing B. And then finally, the last one was from 6 to 9. That's section C. And I'm going to connect those with a line making tool, so that'll make it nice and straight here. So we have section A, section B, and section C. So what do you notice about the three sections of the position versus time graph, and how does that correspond to the motion? So if you take a look at this, we said, again, the order was that the one that had the largest velocity, here we go, the one with the largest velocity was C. So velocity, large, trying to write again, it's not that easy, to small velocity. Our rank or order was, oh, sorry, our order was C. Oh, that's not working the way I wanted to. Okay, let's try this again. So it was, no, I'm still not doing it. Okay, so I'll go back to what I was doing. It is C, and then A, and then B. And what do you notice about those lines compared to kind of the way they look? So what I would say is that the one that is the steepest is C, and the one that is flattest is B, and then sort of A is in between. So that steepness, which is commonly known as slope, so the slope of the line, is representing the velocity on this particular graph. So the steeper the line, the faster it's moving, the greater displacement it has in a smaller amount of time. So that is the concept that we're trying to get out of this. So position versus time graphs, just some general rules. Position versus time graph shows the location of an object at a certain point in time. We can also measure the displacement over a period of time. So like in the first 3 seconds here, it goes from, let me move this back to, I think, making it look a little better. There we go. So in the first 3 minutes of time, it covers, it looks like, around 200 meters. And if we go back to our thing, yeah, that's pretty close. It's a little less than 200, but it's close enough on our graph that we can kind of see that. So you can measure the change in position, and then we just got done speaking about the slope of the position versus time graph is the velocity, or average velocity if you have a changing velocity, but we have a steady velocity. Okay. So again, this is what we were talking about. So let me move this up a little bit. There we go. So from position versus to velocity, so our position versus time graph of faster is steeper, and again, that makes sense. So if we look at this last part, it looks like it rises 300 and it goes over 3, so that would be like a velocity of about 100. This one only goes up about 203, so that's going to be less than 100, and this one is way less than 100 because it looks like it doesn't go up barely at all. It goes up maybe a little above 200, so maybe like 40 in 3 minutes. So it's again, it's the rate. So the slope of the line, that's the velocity. This slide, I think, is useful. It kind of describes the motion and ideas that go along with position versus time graph. So again, on a position versus time graph, I'm going to sketch another one. So position, again, is on the vertical axis, time is on the horizontal. I'm going to graph a line here, and I'm going to ask you to kind of think through what's going on. So it says you can determine the object's position, so like whatever number it's at, that just tells you the position at a certain time. So we're going to be able to read those off. Well, we're going to practice this in a minute. The slope of the line, again, represents the velocity. So velocity is the slope. That's an important concept that you're going to need to use and do on future tests. And then the direction of the motion is also described. So in our picture a couple slides back, if I go back to here, these are all positive slopes. So they are all positive velocities. Positive velocity means, again, it's moving to the right. So if we look at our motion map, at all times it's moving to the right. If you had a negative slope, like I do on this, we would have a negative velocity. So this is, again, positive slope means up and to the right. Negative velocity means down and to the right, so this is moving back to the left. And then for this one, this is supposed to be a horizontal line, even though it maybe is a little up or down. if you are staying at the same position, so the location is the same location, all those like dashed lines that I just made, the velocity would be equal to 0. So that still works with the slope, because if you have a horizontal line, there is no slope. So that means you're stopped. So that seems to work out nicely in this as well. All right, so we're going to practice here on this one, and then we are going to take a break and do a different video, because I want to try to keep the videos a little shorter. I went way long on the first one. So it says, looking at this position versus time graph, we're going to answer some questions. So hopefully you can see this graph okay. And again, position is on the vertical, time is on the horizontal. We are counting by, it looks like, units of 1 going across here, and we're going up to 40 as the highest position to the right. So again, if you wanted, we could turn this into a motion map, but I generally don't do that. I just kind of look at the graph and try to interpret what's going on. So we want to figure out what is the object's position at 2 seconds and 6 seconds. So 2 seconds is here. And I just want to go up until I hit the line, and I'm going to use a different image here. So at 2 seconds, I go up and hit the line, and I'm going to put my smiley face there, and that is where the object is. So I would just go over, and it says 10. So for the first one, at time equal to 0 seconds, x equals positive 10 meters. So the location x is the position. That is the answer to number 1. Let me try to write these out, because I'll type several. There we go. Okay. So at 0 seconds. It wasn't 0 seconds. It was 2 seconds. Sorry, excuse me. So at 2 seconds, the position here is where the smiley face is at positive 10. And then we had another question with that. So at t equal to 6 seconds, x is equal to what value? So let me give you a chance to think about that and read that off the graph. And if you did that, you'd go to 6, and you go up to there, and you'd hit it, and you go over, and that's at 20. So again, not too bad to figure out. Those are just basic kind of concepts, and it's a positive 20 meters. So those are the answers to number 1. Number 2 is asking for what is the time or times when the object's at 20 meters. So x is equal to positive 20 meters, and we want to know when the times are equal to what. So it's kind of the reverse process. So we're going to go and start at 20 and go over until we hit the line. So it looks like there, that section here, and it's a little off. Let me redo that. Okay, this will be a little cleaner. So starting here, it looks like going over. So that little section that I have there, and it looks like that's from 4 to, get rid of the smiley face. It looks like it's from 4 to 6. So 4 to 6 seconds is when it's at a positive 20. And then also you might say, okay, well, it looks like it gets to 20 and hits the 20 down at this 12 mark as well. So I'm going to write all those. So it looks like from 4 to 6 seconds, it's at 20, and at 12 seconds. So that you are allowed to be at a particular instant or place for many seconds of time. So like I'm sitting at my desk now and haven't moved in a while. So I am still here. I'm not breaking any laws of physics, but you can't be at 2 places at once. So like you can't be located at 20 meters and 10 meters at the same amount of time. So that doesn't make sense. So that's why we only had at a certain time 1 position, but you could have many times when you're at the same location. For the next one, it says when you're at 30. So if we do the 30s, and I'll use a different kind of marking. So at 30 here, that's the first time I'm at 30. That appears to be the last time I'm at 30. So if I come down, it looks like 8 and 11. So we'll type those in as our answers or our solutions for that. And hopefully you're following along and doing the same kind of work in your head or writing it down, because I think that is how you learn better when you're watching these videos. So the times when it's at 30, again, we said those are where those pink dots were, so 8 seconds, and it looks like 11 seconds. So far so good. Hopefully everybody's doing okay with that. Question 3 asks for several things here. So it says moving in the positive direction. Then it asks you about moving in a negative direction. And then finally it says when is the object stopped. Okay, so we need to examine moving and think about moving. So when you're moving in the positive direction or negative direction, you're really discussing the velocity. So if you have a positive direction, that's like going to the right. So that would be a positive velocity. So the numbers for the velocity the number for the velocity value would be positive. Moving in the negative direction would be the opposite of that. So you'd have a negative velocity value. And then if you're stopped, just like you're in your car and you're not moving, your car reads that your speed's close to velocity. So we'll talk about that more when we get to that concept again on graphing, but the velocity is 0. All right. So we're looking for when the velocities are positive, negative, and 0. And again, we've looked at position versus time graphs, and we discovered that the velocity is the slope. So we just have to look at the slopes and decide where the slopes are those values. So basically we're looking for anywhere with a positive slope first. So I'm going to highlight some of those. So a positive slope means it's going up and to the right. So that appears to be a positive velocity or a positive slope and positive velocity, and that one seems to be a positive velocity as well. I'm just going to estimate that this is at 10, so I'll put the dot there. So we'll just say it's exactly at 10. So answering the question for the positive velocity part, the times when that occurs at are from 0, it looks like, to about 4 seconds, and then from 6 seconds to, we're going to say that's 10 seconds, even though it's on the graph it's a little bit shorter. Moving in the negative direction, that would be a negative slope. So negative slope, we're going to highlight that section of the graph, so that it's going to be going down to the right. So this blue section here, that is the negative portion of the velocity, negative slope. So that occurs when the time is equal to, it looks like 10 to 12 seconds. And that makes sense because it's moving from a position of 40 down to 20. So the positive ones, it went from 0 to 20 and then 20 to 40. The last part, when it's stopped, velocity is 0. So no velocity or no slope occurs from times equal to 4 to 6 seconds. So it should be staying at the same location, and that's what happened. So like it stopped here at 20 meters for that time. So that horizontal yellow line there, it is not moving. Okay. So so those are the answers to number 3. Number 4 is talking about total distance and total displacement. So we'll talk about distance first because I think distance is easier than displacement, but it actually, I don't think either one is to calculate or solve for in this example. So total distance, again, distance would just be, you would add up all the segments. So add all the lengths. We talked about that last video. So if we add up all the lengths, we're adding like all these different sections where it moved. So, but you don't worry about direction. So in the first one, for this first green section, it goes from 0 to 20 meters. So that would be 20 meters. And then from 4 to 6 seconds, that next segment, it's not doing anything, so it doesn't travel anything. It's stopped, it's 0 meters. For the next one, it goes from 20 to 40, so that's another 20 meters. And then the last one, it's going from 40 to 20, so you move back in the opposite direction, but you don't worry about the negative there because it's not a vector quantity, it doesn't worry about direction. So we just have to add all those lengths up. So 20 plus 0 plus 20 plus 20 gives you 60 meters. And again, 60 meters is just the total length. So we'll go through some other examples in class in person when we talk about how to discuss that. For total displacement, again is delta or triangle x. So let me see if I can get this real quick so I can have the right notation for you guys. There it is. Okay, so we're working horizontally, so that's why we have x there, but triangle means change in, so it's going to be the final location minus the initial location. That is how you always find displacement. So your final spot minus your initial spot. So looking at the final spot, that's at here at this point. So we're at 12 seconds. We go over and we're at 20 meters, and it's a positive 20. And then we're going to subtract the initial position. So if we go back to the initial position, it says it starts at 0. So 0 meters, and it'd be 20 minus 0, which is a positive 20 meters. And that is the total displacement. So it's saying it started at 0 and it went to 20, and that's fine. That's where it ended up, comparing where it starts to where it finishes, which is what displacement does. So this example is supposed to illustrate that displacement and distance are not always the same. For the last thing, we're going to calculate those average velocities. So we already determined whether the velocity is positive or negative, but we also want to calculate the number or the value for that. So for the first one, we're going to find the slope when the time is between 0 and 4 seconds. So when that happened, we need to find the slope of the line. So I like drawing in the slopes here. So we're rising from 0 to 20. I'm going to change this to an arrow and try it again. So we're rising from 0 to 20, and then we're going over whatever amount of time that is. So for the first one here, we're going positive 20 meters, and we're going to divide that by the run across, which is 4 seconds of time. So if I divide positive 20 by 4, I get a positive 5 meters per second. And we said that makes sense because it should be moving to the right there, and it's got a positive velocity. For the next one, which it asked for, was 4 to 6. 4 to 6, you can look at this line, and it's a horizontal line, so there's really no slope. It doesn't change its position at all. It's not going up or down, so that's 0 meters. Whoops, 0 meters divided by the amount of time, which is 2 seconds. So 0 divided by 2 is going to get you 0 meters per second, and we expected that because we said it was stopped. The next one, I'm going to go ahead and do 6 to 11, or 6 to 10. No, that's 11. 6 to 10, sorry. 6 to 10 seconds. So again, we're looking at the rise and the run. So if we go up, how much it goes up. So starting at 20, it goes up to 40. So that's a gain of 20. And we're going over. It's going from 6 to 10. So that's fine. So the rise would be a plus 20 meters. And we're going to divide that by the amount of time. So 6 to 10 is 4 seconds again. So we're going to get the same answer, positive 5 meters per second for that one. For the last one, I'm going to do 10 to 12. It says 11 to 12 on your paper, but let's go ahead and do 10 to 12. The line is the same line, so if I did 11 to 12, I could start here at 30 and go down to 20 and figure out the slope there, but I'm going to figure it out for the entire line. Since it's a line and it's not broken, it has the same slope throughout the whole line segment. So that's what we're doing. So we're starting at 40 and we're dropping to 20. So that's going down negative 20 meters. And then for the last part, it's going from 10 to 12 seconds, so that'd be 2 seconds, and that'll get you a negative 10 meters per second. So if we were ranking the one with the largest magnitude or size of velocity, it's that last segment because it covers 20 meters in 2 seconds, as opposed to the other ones that are moving where it takes 4 seconds to cover the 20 meters. So there you go. Those are the answers to that sheet, and I'm going to stop there because the video is getting long. So we'll come back with velocity versus time graphs.